Hello everyone. From this lecture, we will be starting Chapter 8, Exergy. Till the last lecture, we have completed our second law, thermodynamics and entropy analysis. Okay. So first of all, we will discuss what is entropy. Sorry, what is Exergy? Okay. So Exergy G of a system at a given state is defined as the maximum work that can be extracted from it till it reaches the state of thermal equilibrium. Sorry, not thermal equilibrium, thermodynamic equilibrium with its surrounding. Okay, so the exergy of a system is given at a given state. So exergy is always defined at a given state of the system. It is defined as the maximum work that can be extracted from it till the surface the system reaches the state of thermal equilibrium with the surrounding. Okay, so this concept of exergy is very important. Whether it's it is very important in case of both energy producing or energy consuming devices. Okay, so when we study the first law of thermodynamics, we studied that first law provide us with the energy analysis of the system. Okay, and when we studied the second law, in second law we have seen that the second law emphasizes more on the form of energy that is not of same quality. It means that it always tell us that energy will always degrade if we try to conserve it. Okay, so both first and second law are analysis. Okay, now both the first law and second law required this exergy. Okay, so when we carry exergy analysis, we require both first and second law here. In this complete chapter, we will be requiring both laws. And uh, what is the purpose of studying this chapter? We have to make every system more efficient. Okay, so for that we have to obtain the maximum work possible from our system. Okay, so for that we basically study the exergy. Okay, now the first topic we will be looking into is dead state. What is the dead state? Okay, so for any substance, when its pressure increases, let's say for there is any substance for which if the pressure increases, the volume decreases. Okay, not for any substance, for every substance it happens. Okay, uh, when the pressure of substance increases, its volume decreases, but if the pressure of substance decreases, its volume will also decrease. Okay, what is another thing? Another thing is that, let's say that if the temperature of the system increases, what will happen if temperature of the system increases? Sorry, here when the pressure decreases, the volume will increase. Okay, when temperature of system increases, its entropy also increases. We know na, uh, like at higher temperature, the higher the temperature, higher will be entropy. Okay, if any substance is kept at higher temperature, its entropy will be higher, and if the same substance is kept at lower temperature, the entropy will be lower. Okay, so from here we can see that dp by dv for any process must be less than 0. Okay, so we can say that for any system, like the slope of PV diagram for any process must be negative. Okay, so whenever we draw our PV curve, so we always see the curves like this. Okay, or at max it turns out to be 0. Okay, like a uh, constant pressure process. Okay, sorry, for constant pressure process, the like del p by del v change in pressure with respect to since there is no change, it is 0. But if we consider constant volume process, this is constant volume process. For this, since there is no change in the volume, the del p by del v will be infinity. And okay, so basically whenever we see the process, our del p by del v should be always be less than 0. Okay, now if we talk about in ts curve we can see that del t by del s must be always greater than 0, because the temperature increases, entropy also increases, and if temperature decreases, entropy also decreases. Okay, so whenever we draw ts curve, so its curve is, it's always a positive curve. Okay, like if we draw constant volume curve or constant pressure curve here, so it will always have a positive slope. Okay, now it's for expansion or contraction, we can uh, look into this later. Okay, now let's say that p node and t node be the ambient pressure and temperature of the surrounding. So let's say there is a system, so this is our system. Okay, and let's say it is at like pressure p, volume v, temperature t. Okay, and the surrounding having the pressure p node and temperature t node. Okay, let's remove the volume term. Okay, let's consider pressure and temperature are p and t. Okay, now what will happen if a system is at pressure p and t and the surrounding is temperature at pressure p node and t node. Okay, now so what will happen, there always exist an opportunity, like this system can always produce some work. Okay, however, when the state of like the system will draw closer and closer to the ambient temperature, this opportunity decreases. Okay, and when the system reaches in equilibrium with the surrounding, what will happen in that case? In that case, there won't be any work done. Okay, now when the system reaches in equilibrium, we can say that this p and t value will be equal to p naught, and there also must be our chemical equilibrium. We know that both in thermodynamic equilibrium, it will mean that 3 points. First is thermal equilibrium, second is chemical equilibrium, third is mechanical equilibrium. Okay, so the system will have like zero velocity. Okay, and it will be at its minimum potential energy. Okay, this state, okay, when the it is in thermodynamic equilibrium with the surrounding, is known as dead state. Okay, so this state which you mentioned, which we have seen here, is known as dead state. Okay, now the properties which are used to define the dead state is are often described by using 0 as a subscript. Okay, so like we describe p node and t node. Okay, or if we describe enthalpy, we will write h node. If we define entropy, we will write s node. Okay, next, now since I've already told you that the state of system with respect to state of surrounding does represent how much work it can be obtained from the system. Okay, now uh, like we can say here that in any change in the system from a dead state dead state is measure of exergy. Okay, so there is one more definition of exergy. Okay, the change in state from the dead state. Okay, or and this exergy is already I think already mentioned. If not, then I will write it here. This exergy is also known as available energy. Okay, available energy or availability or irreversibility. Okay, now we will like see all the terms in the this chapter further. Okay, and this exergy is also called like maximum work that can be obtained from the system. Okay, so the exergy of this system at temperature P and T, when the surrounding is at P node and T node, what will it represent? It will represent the exergy value, that is the maximum work that we can extract from the system before it reaches the dead state, that is in thermodynamic equilibrium with surrounding. Okay, so in the definition, when we like mentioned, the exergy of a system is given at a given state is defined as the maximum work that can be obtained extracted from it till from it till it reaches the state of thermodynamic equilibrium with its surrounding, or we can also say that that is it reaches. All this term is written as can be written as dead state. Okay, so the to maximum work that can be extracted from it till it reaches the dead state. Okay, now uh, as I have mentioned earlier, the system like here the a system is said to be in thermodynamic equilibrium with the surrounding only when it attains the dead state. Okay, now let me tell you some process examples, the processes which can be considered reversible or irreversible. Okay, and similarly we will also write the processes which are considered reversible. Okay, okay, so and this is reversible. Okay, so we will see both reversible and irreversible processes simultaneously. Okay, so here is the first irreversible process, a process which involves friction, viscous forces, viscous forces, electric resistance, electric resistance, and inelastic collisions. Inelastic collisions. These type of processes are called irreversible processes. Okay. Now the second point is if the heat transfer between the system. I mean heat transfer is through finite temperature difference. Okay, like if we are transferring heat from one surface to one body to another, and there is finite value of temperature difference, like let's say one is at uh, 10 degree Celsius, another is at 0 degree Celsius. So there the process of heat transfer will be irreversible. Okay, next, we can third point we can mention is constant volume, constant volume, constant pressure, or polytropic heat transfer to gas at single temperature. Okay, so let's say that there is a system. Let's say this is a cylinder piston arrangement, and the gas heated as, let's say, 300 Kelvin, and it is heated with the help of source, let's say at 500 Kelvin. Okay, and this gas is heated from 500 to 500 Kelvin, 300 Kelvin to 500 Kelvin. Okay, so we can see that like the sink is always like the source is always at 500 Kelvin. Okay, but the or we can draw it like this. It is always at 500 Kelvin. The source sink is, and the system's temperature is the like increasing to from 300 to 500. Okay, now we can see that not at every point, like here it is a finite difference of temperature, here finite difference temperature. Okay, only at near the end the temperature difference is not finite. Okay, so since as we have discussed in point number 2, this process will also be an irreversible. Okay, next, fourth point we can talk about is uh, free or unrestrained expansion. Okay, fifth point we can talk is mixing of dissimilar fluid. Okay, sixth point we can talk about is magnetization. Magnetization and demagnetization. Showing hysteresis. You should have already like studied hysteresis in class 12th. I won't be mentioning it here. Okay, if you want to like know about what is hysteresis, magnetization, demagnetization, you can like google it or see some videos on YouTube. Okay, next point number 7th, we can also say that elongation of bar beyond elastic region or elastic limit, we can say. Okay, so up to elastic limit, the shaft or the bar can always like regain its original structure. Okay, so that will be a reversible process. But what happens after like elastic limit, it can't like regain its shape. Okay, so at that point it will be irreversible. Okay, now if we like talk about reversible processes, so first we can like say that if the heat if the temperature difference for heat transfer, like it is in point number second, here it was finite different temperature difference, and here if we say this for this temperature difference for this heat transfer is close to zero, then the process will be reversible. Okay, similarly we can say that considering this only, isothermal processes are reversible process. Okay, and why it is like this? Because the heat transfer temperature difference is always zero. Okay, now like here we can like say that this, if the isothermal is carried by delta t tending to zero, so it should be considered as reversible. But in case here, let's say that we have also like gone the isothermal process, like this only, as I mentioned, constant pressure, constant volume, and polytropic. Here we can also say that isothermal, T is equal to constant, like heat transfer to at a single temperature. Still, if like this is T is equal to constant is achieved by let's say system that is at a constant temperature. Okay, let's say this is at 500 Kelvin. Now to maintain this temperature 300 Kelvin, we are using the sink, let's say at 500 Kelvin. So we will like see this here. Although the temperature of the system is always at 300 and the sink is always at 500 Kelvin, but there is some finite difference, finite temperature difference available here. Okay, so the system will be irreversible. Okay. Now moving to next point for reversible process. So we can say that all the phase change processes are reversible. Like boiling, or if we talk about the solidification, we can always like reverse the process. Okay, we can always like melt the ice into water, and we can always condense the steam into water again. Okay, so these all processes are reversible processes. Okay, point number 4. Point number 4 is like any heat transfer process is reversible if, okay, all the heat processes are reversible if like the process is carried out by using infinite reservoirs. If process is carried by infinite reservoirs. Okay, what does infinite reservoir represent? That our delta T tend to 0. Okay, like if we have to create the temperature difference of 100 degrees, so we will create it in infinite number of stages. Okay, just like a quasi-static process. Okay, so point of fifth, if we talk about, we can say that mixing of, like here we had talked about mixing of dissimilar fluids. Here it is a mixing of similar fluids or similar substances or fluids initially at same state. Okay, it must be initially at same state. Okay, if state is different, then the process will be irreversible. Okay, and as in last we talked about elongation of bar beyond elastic limit is irreversible. So elongation of bar within elastic limit is reversible. Okay, next there is one more example, like if we talk about compression of spring. So if we release the spring, it will regain its original shape and size. Okay, so these examples can be like you should know that the examples are your reversible and irreversible processes. And there of course there can be many more examples similar way. If it is asked in exam, you can like see if the given, like if it in the following, if it falls in the following points, you can directly answer it, and if not, you can think about those examples. If there is some like temperature loss or loss to the surrounding heat generated inside the system. Okay, finite temperature difference is available. Okay, in similar way you can do those questions. Okay, now we will be moving to our next. In last lecture, I have already defined you about what is a Carnot cycle. Okay, so in this lecture, I will be drawing the Carnot cycle on a TS diagram. I think in last I have already drawn it on PV diagram. Okay, so let's say that there is a system. Okay, which receives heat. Sorry, this is a TS cycle. Okay, which receives heat at temperature, let's say T1. Which receives heat, let's say this is our temperature, let's say this is temperature T, this is our uh, temperature T node, which is also a dead state temperature or surrounding temperature. Okay, Now if I talk about the Carnot cycle, this will be process 1 to 2, 2 to 3, 3 to 4, 4 to 1. So process 1 to 2 is, what should be process 1 to 2? It is, this is our isothermal compression. Okay, this is, or sorry, not isothermal compression, this is our isothermal heat addition. Okay, and Q amount of heat is provided to the system. Okay, 2 to 3 is, this is our, in process 2 to 3 we can see that like temperature of the system is decreasing. So this is, so let me write it here, process 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Okay, I will write what are these processes here again. Okay, so process 1 to 2 is reversible isothermal heat addition. Okay, process 2 to 3 is reversible adiabatic expansion, reversible adiabatic. Okay, you can see that since entropy remains constant at both points, so this will be an asentropic process, so adiabatic process. And since it is adiabatic, and here also you can see the temperature of the system is decreasing, so it must be expansion. Okay, expansion. 3 to 4 is reversible isothermal heat rejection. Okay, here the amount of heat, like say Q node, is rejected, or QR is rejected. Okay, okay, next we can and let's say this QS heat is supplied. Okay, next process 4 to 1, you can write it as reversible adiabatic compression. Okay, now next we will use, like you should remember that this is a Carnot cycle. Okay, let me, this is our Carnot cycle. Okay, cycle. Okay, now we will like this, use this cycle frequently in our next few topics. Okay, now I will start discussing the available energy in the various processes, or you can say that maximum work available. Okay, or exergy available during various situations. Okay, so I will write available energy, or you can say exergy in various situations. Okay, so the first situation I will be discussing is thermal energy at a single temperature. At a single temperature. Okay, now so this is what, this is a thermal like we can say that the available energy with a reservoir. So thermal energy at a single temperature means what, like this thermal reservoir is always as a single temperature. Okay, and it contains infinite amount of thermal energy. Okay, so we can use it to calculate if we want to calculate the available energy, what amount of energy is available with the particular thermal reservoir, so we can calculate it from here. Okay, now let's see like we can, okay, so this is our, let's say, a heat engine example. Okay, where it is interacting with a thermal reservoir. Let's say this is temperature T. Okay, let's say this is temperature T, and it is receiving heat from temperature T. Okay, and heat received is Q. Okay, let's say it is rejecting heat to the surrounding, which is temperature T naught, dead state, as I mentioned earlier. Okay, now let's say this is producing some amount of work. Okay, so as I used in Carnot cycle, let use the same sign conventions, QS and QR. Okay, here also QR. Okay, now if we want to calculate the available energy that it has, or the maximum work that it can produce. Okay, so using the Carnot cycle, okay, here I can also write one equation. Let me write it here first. So I can write that this amount of this QS is equal to, or I will directly explain it into here only. Okay, so let me like copy this TS diagram. We will use it in this question. Okay, copy and we will paste it here. Okay, so let's say that this heat engine will be acting as a Carnot cycle. Okay, this is a reversible heat engine. Okay, so we can see from like look into from here, I can mention here that this change, entropy change, this term is will should be known as delta S. Let's say it is delta S, so I can write delta S, or we can say it, write it in a small letter. Delta S is specific entropy, and this will be equal to S2 minus S1 is equal to S3 minus S4. Okay, now if I want to write like QS, Q supplied to the engine, Q supplied, I can write it as T times of we know that delta S is equal to del Q by T. Okay, so if the system like here I can write it as QS is equal to T times of delta S. Okay, and QR is equal to T naught times of delta S. Okay, now we will use this in like finding the maximum work from the thermal reservoir. Okay, so whenever from any system, like say that we have been provided with any system and we have to find what is the maximum amount of work that the system can be produce. Okay, so we will directly like attach a with the heat engine with the our system. Okay, like here we attach the this heat exchanger with, sorry, this complete engine with our thermal reservoir, that is, as I mentioned, thermal energy at a single temperature. Okay, which is interacting with our surrounding. Okay, now what I have to do, like I can write the efficiency of an engine is equal to 1 minus T naught by T from for a reversible Carnot engine. Okay, and we can further equate it as W max upon Q supplied. Okay, so from here I can write my W max is equal to 1 minus T naught minus T times of QS. Okay, and I can like substitute the value of QS, or I can like directly open it first. So I will write uh, QS minus T naught times of QS by T. Okay, from here I can write QS is equal to T delta S. Okay, as I written as here, QS is equal to delta S minus T naught times of I can write QS by T is equal to delta S again. Okay, I hope you get it. In next step, what I can do, I can write W max, or I can also write it as available energy. Okay, and Exergy is generally also denoted with X. Okay, so from here I can write T times of, for delta S I can write it as S2 minus S1, S2 minus S1. Okay, I mentioned here S2 minus S1 minus T naught times of, here delta S I can also mention S2 minus S1 or S3 minus S3 S4, but since the T naught temperature is at like belong to 3 and 4 points, I will directly use like 3 and 4 points only. Okay, S4. Okay, so this what is this amount is the total maximum amount of work that can be obtained from a thermal reservoir. Okay, or a system at a having thermal energy at a single temperature. Okay, we can also like reduce it further. Let me write it. Now what do you think, like since I already said that these both are equal, so what I can do is I can directly write it as T minus T naught times of delta S. Okay, or what else we can, like, if even if we don't write it like this, from here we can directly mention that this term and this term. So from here we can see that our QS value is T delta S, which is this, and QR is T naught delta S. Okay, So here we get that this available energy will be equal to Qs minus Qr. Okay. Now this Qr, our rejected heat, is also known as unavailable energy. Unavailable energy. Okay. Or it is also called energy. Eh, energy. Okay. So we can write it here. Available energy is equal to Qs time minus unavailable energy. Okay. Now let's talk about an example. So we will take this diagram only. Okay, let me paste it here. Okay, so in this diagram, let me delete a few things first. Okay, so let's say that this is a process which is 1, 2, 3 and 4. Okay, now what happens that let's say that 1,000 kilojoule of heat is supplied to the system. Okay, so let's say that Qs is equal to 1,000 joule. Okay, now also let's assume that this higher temperature is at 600 Kelvin, and the dead state, that is our surrounding state, is 300 Kelvin. Okay, T node is equal to 600 Kelvin. Okay, let's say this is temperature T1 is equal to 600 Kelvin. Okay, now let's say that we have to provide the same amount of heat but at a lower temperature. Let's say that we choose that our system like we have stored the amount of heat of 100,000 joule at 600 Kelvin, but with due time the same energy, we get the same energy, let's say at 400 Kelvin. So let's say T2 is equal to 400 Kelvin. Okay, now since the amount of energy is same, so let's say that is starting point from here, we started the heat supply. Okay, so we know that Qs is equal to T delta S. Okay, now since I mentioned here Qs equal to 1000 joule and this is the delta S here. Okay, let me mention it here. This is our delta S. Okay, now let's say that we have to supply same amount of heat at lower temperature. Okay, since temperature is lower, so our delta S value must be increasing to maintain the same heat. Okay, so when we supply the heat, we have to like supply it to a higher entropy change. Okay, now let me move one thing more. Let's say this is S. Okay, so when we moved from, or we can let me throw it here again. Okay, so let's say that this is our system. Okay, so when we okay, so let's say that when we decrease the when we supplied the same heat at lower temperature, our change in entropy of the system will also increase with it. Okay, so let's say this new change in entropy as delta S dash. Okay, from here what we can say that earlier this amount of heat, this was the QR. Okay, which was rejected. Okay, now after we decrease the supply temperature, okay, again after supply the temperature was still Q is equal to the heat was supplied was still 1000 joule but low temperature. which result in our increase in change in entropy. Okay, so here we can see that, let's say this is our QR. Okay, or we can write, let me write in another way. So let's say this area is X, and let's say this area is Y. Okay, so initially when our uh, temperature supply heat temperature was at 600 Kelvin, we get QR at the rate 600 Kelvin. 600 Kelvin is equal to X. This was the amount of heat which is rejected at 600 Kelvin. Now since we have decreased the supply at 400 Kelvin, so Q rejected at 400 Kelvin is equal to our X plus Y. So from here we can see that our available energy from the system, which we represented by Qs minus Qr, will become, for let's say this is for system 1, so for second system it becomes available energy becomes Qs minus Qr dash. Okay, so this Qr dash is greater than Qr. Here we get Qs minus X, and here we get Qs minus X plus Y. Okay, so from here we can say that this amount, this area, this amount Y is the increase in unavailable energy. Okay, and we can also say then since Q is less than X plus Y, so sorry, X is less than X plus Y, so we can say that available energy at higher temperature is greater than available energy at the rate lower temperature. Okay, and since I also already mentioned that this Y amount of heat is the increase in unavailable energy of the system. Okay, now here we can define an Exergy function. Which will be represented by phi, and this like this Exergy function represent the state of represents the available energy at a state. Okay, so we can write Exergy function for thermal energy at a single temperature. We can write it as so from here we see that our W max value is equal to 1 minus T naught upon T into Qs. So we can write phi is equal to Q into 1 minus, or we can write it as Qs into 1 minus T naught by T. Okay, now if we have to like calculate what should be the change in available energy from state 1 to 2, let's say we have given the two states, state 1 and state 2, and we have to calculate change in available energy. So we can directly calculate the change in energy function, which will be equal to Qs into 1 minus T naught by T1 minus Qs into 1 minus T naught by T2. Okay, now in the above discussed example, let's say in this example, if we see the cycle 1 2 3 4, and let's say that the another cycle is 1 dash 2 dash 2 dash 3 dash and 4 dash. So we will be talking about all these cycles. Okay, so if we talk about our cycle 1 2 3 4, this here is the maximum amount of work that we can obtain. Okay, as I have also written it here. So this amount is the maximum amount of work that we can obtain. But when we decrease the temperature of the heat supplied at 400 Kelvin, our work done obtained is also decreased, because here you can see that since is uh, T1 is greater than T2. Okay, if we talk about this, then we can see from here that phi1 is greater than phi2. If this value is larger, then this complete value will be smaller. Okay, this value, sorry, if this value is larger, then this value will be smaller, and this complete value will be again be larger. Okay, and similarly this value is smaller, then this value will be larger, and then this 1 minus T naught by T2 value will be smaller. So we get from here that if T1, or let me write it with pen, if T1 is greater than, or not if, it is since I have already defined it, T1 is greater than T2, so we can say that phi 1 is greater than phi 2. Okay, now since so we have already seen that from here we can see that if we supplied a same amount of heat at 600 Kelvin, the amount of work we obtain is greater than that of what we supply at 400 Kelvin. Okay, so it means that this amount of work we lost, this amount of work, area corresponding temperature from 600 to 400, in moving from 400 Kelvin energy transfer to 300 Kelvin. Okay, so this was our initial work, total area, if we complete cycle consider cycle 1 2 3 4. Now this is our final area when we consider the cycle 1 2 dash 3 dash 4 dash. Okay, so some amount of work obtained is less, and how much work is obtained is less. This particular y amount represents the decrease in obtainable work from the system. Okay, moving to next topic. So the next analysis we'll be seeing about finite mass of solid or liquid. Okay, let's say that as a system having mass m, heat capacity C, and its initial temperature is T1. Okay, now we have to calculate the maximum work possible from the system. We should always attach a heat engine with this. Okay, let's say that the sink temperature of the engine is T node, which will be our steady state and also the surrounding temperature. And this temperature, let's say at any point the temperature of the system is at point T. From here the heat will be supplied at particular temperature T. Okay, and the system itself will change from temperature T1 to temperature T node when it reaches the equilibrium. Okay, now let's assume for a small heat transfer, let's say that del Q is a small heat transfer from the system to the engine, and this will be equal to mc dt. But here we can see that this change in temperature dt, T2 minus Tv, T1 will be negative, because T1 is greater than T node. Okay, so at any point temperature T will be greater than the surrounding temperature or steady state temperature. So this here we will multiply by -1 to clarify it. Okay, next let's say that we obtained the work delta W from the system, and of course the engine is a reversible. Okay, now we can write work obtained will be equal to del Q times of 1 minus T node by T. Okay, now here T represent the temperature of the system at any point of time. Okay, we can write delta Q is equal to -1 times of mc dt times of 1 minus T node by T. Okay, now if we integrate it, so we will get del Q is equal to integration del Q is equal to minus mc times of integration of 1 minus T node by T times of dt. Okay, and this will be from temperature T1 to T node. Okay, so we will get work done maximum is equal to, or we can also call it available energy. Okay, and its value will be equal to mc. Here we will write dt, we will write t naught minus t1, and this term we will get minus t naught times of ln t naught by t1. Okay, now if we like send the minus inside, we will get mc times of t1 minus, or I can like write it as t1 minus t naught plus or minus t naught sorry mc t naught times of ln t1 by t naught. Okay, so this term here we can call it, this term as q net. Okay, so if we consider the system, so net heat which can be sent to this engine will be equal to mc delta t, that is t1 minus t naught. Okay, and this is exactly the same term, and this term here can be written as t naught times of, let's write t naught first. So the left term is mc ln t1 by t2, t1 by t naught. Okay, now this term here represent the change in entropy of the finite mass, as we studied in the last chapter. Okay, so here we can write the available energy is equal to u1 minus u node minus t node times of s1 minus s node. So, oh sorry, this should be capital S because mass is included here, s2 minus s1, sorry, or s1 minus s node. Okay, now here we can define, and of course this part here will be unavailable energy. Okay, so again available energy can be written as q net, this is q net minus unavailable energy. Okay, now again we can take a phi as an energy function here, Exergy function, which can be defined as u minus t node s. Okay, now if I want to calculate the available energy for the system, between system and the surrounding, so I can calculate it as u1 minus u node minus t node times of s1 minus s node, which is exactly this equation. If I want to calculate between two different states, okay, I can calculate it as u1 minus u2 minus t node times of s1 minus s2. Okay, like this we can do here. Now if we move to next question,